Boo 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 boo. 11111. Hello, everybody. I'm Dr. David Hanak, and welcome to this live session on LinkedIn. So, hopefully, you can hear me and you can see me. I think you should be able to see me. And just wanted to check because previously that was total disaster. So, let me know in the comment if you can hear me before I start. And I think you can hear me because just heard myself. Um, okay, I think the technical issues are resolved right now, and we should be able to hear ourselves, and I should be able to see your comments as well. So if you have any questions about, direct air capture, about my work, or green energy transition in general, feel free to use the chat below this video. And yeah, let's crack on. Just final verification. Let me just double check if everything is okay. Okay, you can hear me, you can see me, so let's get started. Okay, so today I wanted to talk about direct air capture, mostly because I had a couple of good discussions recently with you on LinkedIn and any other platforms, and just thought, why don't we actually discuss direct air capture in this form, in the form of the live video, mostly because what I want to do is want to clarify a couple of points about direct air capture, want to talk about what direct air capture is, and what are the challenges and opportunities. So let's get started. So, as you know, I'm David Hanak, a senior lecturer in energy and process engineering at Cranfield University, and my mission is to actually make sure that we transition to green energy economy within couple of years, hopefully. So today I want to talk about direct air capture and why we need that, what it is, and what are the challenges. So let me firstly tell you, why do we need direct air capture? Why it's important to have direct air capture or greenhouse gas removal technologies in the first place? So the main misconception about greenhouse gas removal technologies, is that they will replace any other technologies, right? So regardless of whether we have GGR or not, we first need to decarbonize our economy as much as possible. So we need hydrogen, we need renewables, we need nuclear, and we need carbon capture in different mixes of those technologies, depending on the country resources, of course. But we need all of those technologies, all of those big guns, to actually decarbonize our economy. So what it is, about what is about the greenhouse gas removal? Why do we need that? Well, if we delay the kind of decarbonization, if we delay deployment of carbon capture storage, hydrogen technologies, renewables, then by 2050 or 2060, we wouldn't become net zero emitters. So we wouldn't meet our emission reduction targets. So that's where the greenhouse gas removal technologies can play a role in meeting our decarbonization targets, because essentially they can remove CO2 directly from the air, CO2 and any other greenhouse gases. They can remove it directly from the air. So just to clarify, we first have to decarbonize our economy as much as possible before we can rely on GGRs, on greenhouse gas removal technologies. And even if we do our best, we deploy carbon capture, renewables, hydrogen, we might still have some small areas where we cannot decarbonize, mostly because some of the industries are distributed, like transportation. It might be difficult to electrify everything or switch to synthetic fuels. So that's where potentially we might actually have the requirement for direct air capture. If you look at the report from the Royal Society, they estimated that we will need about 810 gigatons of CO2 removals by 2100. So that's quite significant amount of direct greenhouse gas removals, and that's why my work actually, as a part of my work, I decided to focus on this issue. So what is direct air capture? Well, direct air capture works in a very similar way to trees, and as you know, I love trees. I support planting trees, but we have to be realistic about how much we can actually achieve with planting trees. So we need to have alternatives. So direct air capture works as a kind of alternative engineered solution that removes much more CO2 than a single tree. So looking at the technology overview, here you can see the supply chain or direct air capture chain. So what we start with is the most difficult step, of course. We start with removing CO2 out of the air. And that's the challenge, mostly because CO2 concentration in the air is currently at about 415 ppm, and that's very low. And any kind of separation, any kind of chemical or physical separation at that level of impurity, then it's very difficult, very energy intensive. That's why most of the research that we do actually focus on developing new materials, developing new ways to actually capture carbon dioxide from the air, and developing new equipment. And that's the most difficult part. So once you actually capture CO2 from the air in the air contactor, you need to release that. And that's second part of the capture process. So first part is removing CO2 from the air in the air contactor, where the carbon capture material actually gets in contact with the carbon dioxide in the air, and then you have to release that carbon dioxide from that material. And that can be done using either electricity or heat or pressure difference or moisture difference. Again, that step is fairly energy intensive as well, depending on the layout of the plant that you might want to consider. But this is something we already do for carbon capture, mostly because, once you capture CO2, the regeneration part is fairly similar between direct air capture and, for example, carbon capture from fossil fuel plants. So this is something that we've already started developing our expertise 20 years ago or even further. So once you actually remove CO2 and you kind of release that from the capture material, it will have high purity, and then you have different options to actually use it. So you can use it for chemicals and fuels materials, fuel production, and that actually leads to net zero materials or synthetic fuels that potentially have net zero effect on the environment, because you capture CO2 and then you kind of use that fuel to to power your airplanes or cars or any other sort of combustion technologies that use fuels right now. And that same CO2 that was taken from the air will be released to the air. So at best, this technology will be carbon neutral. Another alternative, which is a little bit better from the climate perspective, is locking CO2 in sort of building materials, cement, all of this stuff. EOR is something that is being considered right now for direct air capture projects and carbon capture projects in principle, but personally I'm not a fan of this solution because, well, you use that CO2, you spend that energy to produce that CO2 from the air, and then you pump even more CO2 into the atmosphere from oil combustion and processing. So direct air capture, enhanced oil recovery, I'm not a fan, but just wanted to give you a full picture. And of course, that's the utilization part of what we can do with CO2. But another opportunity is to actually store it underground, but we need to make sure that there is enough storage capacity to actually do it. Let me talk about the capture technologies because that's what my expertise is in right now, and this is something I'm very passionate about. So in terms of direct air capture, we have two main archetypes that people talk about, and that's high temperature capture and low temperature capture. So high temperature technology, like the carbon engineering concept, relies on established process. Like you have established craft process where you use sodium hydroxide to actually capture CO2 from the air. Well, sodium hydroxide, also potassium hydroxide. And you produce calcium carbonate, and that you produce sodium carbonate, and that sodium carbonate is regenerated using calcium hydroxide in the craft process. This technology, as you can see, uses natural materials, which is quite promising, uses existing equipment to some extent. The air conductor was based on the cooling tower, so that's kind of modification of the existing equipment, which is very good. The only challenge and opportunity at the same time is that the regeneration of sorbent requires high temperature. So in the calciner, you have calcium carbonate, which you have to calcine at 900 plus degrees Celsius, which requires combustion of fuel. And that's the main challenge of that technology, because you have to either use fossil fuels to actually run it, or any sort of green fuel like biofuels, biomass or so. There is also potential to integrate that with solar energy, but that would add to costs quite significantly, I think. Anyway, this high-grade heat, of course, it's challenged to provide it because it's high temperature, but there is also an opportunity on the other side because you can integrate the waste heat recovery system and produce useful amount of energy out of that process. On another end, we have low temperature direct air capture technologies. For example, the ones that are developed by Climeworks or Global Thermostat. And these technologies utilize kind of amine-based sorbents or resins to actually capture CO2. The operating principle is a little bit different because in this case you can have a single reactor that captures CO2, and once your sorbent or your capture material is saturated, you switch the conditions in the reactor and you release CO2. So it's kind of either temperature swing or pressure swing adsorption. Also, there is a potential to do moisture swing adsorption where you actually change the moisture content, and by doing so you kind of regenerate the sorbent as well. The benefit of that technology definitely is that it's a low temperature system. So it requires temperatures of about 80 to 100 degrees Celsius, which makes it good for retrofitting within the existing industrial systems, for example, where you have an excess waste heat. Or potentially it can be kind of integrated with the geothermal energy systems. Comparing those two archetypes, so I kind of collected data for those three companies that actually do carbon direct air capture right now. So you can have a look at what are the main differences, and the main difference, of course, is operating temperatures. So you have 900 versus 100-ish degrees Celsius for low temperature direct air capture technology. The difference in purity I wanted to emphasize is, for low temperature direct air capture, you get in principle higher purity because you don't have any combustion products within your CO2 stream. For high temperature systems, you would have combustion products if your energy in the calcination is provided by oxy-combustion of fuels. Energy requirements are broadly fairly similar. Of course, for Climeworks, I would need to add a range as well, but this will be somewhere between these two numbers. The only difference is that carbon engineering system or high temperature system is a continuous process, so it's probably more scalable in my opinion. Unit size can be bigger, while for low temperature systems you have cycles. So you have a cycling process where you alternate between adsorption and desorption of CO2. Of course, there is an opportunity to put several units in parallel that actually, in series, that actually use capture CO2 and and ensure that you have continuous supply of CO2. Now, costs, that's quite significant because everyone keeps talking about energy use and the complexity of the processes, but at the end of the day, we all need to understand how the economics of that process will work. So the low numbers in my table, the lower end numbers, actually refer to the estimates for within the next 20, 30 years. So we actually assume that those costs will go down as we start to learn the technology, as we start to understand how to optimize it, and we come up with new designs. So right now, direct air capture costs, I would say, are between 250 to 500 euro per ton of CO2. And this is quite high compared to 50 to 80 euro per ton of CO2 estimated for CO2 from coal-fired plants or gas-fired plants, for example. However, there are some niche applications that actually pay for CO2 more than 350 euro per ton of CO2 right now. So definitely there is market for CO2 right now, but we need to actually drive the efforts to actually reduce the cost by optimizing sorbents, developing new materials, developing new plant layouts and equipment for direct air capture. So in terms of comparison, high-level comparison, this is my personal view of how those technologies compare. So high-temperature systems, in my view, are a little bit more scalable than the low-temperature systems. So definitely different markets for those. Energy requirement in terms of the grade of heat. Of course, the low temperature is better because you can collocate with other systems. High temperature, again, it's more energy intensive in terms of the energy grade, but then you can recover part of that energy as a part of the wider energy system. Purity, fairly comparable, again, depending on which technology you're going for. Capital costs, I would see the low temperature will be a little bit cheaper than the high temperature, mostly because you have less reactors and you don't really have to have the combustion and all of this stuff. In terms of demonstration, I think the low temperature is a little bit better further right now, more spread, more demonstration plants than the high temperature, but hopefully we see more of those demonstrations soon. Now that we know about how to capture it, I just wanted to emphasize there are existing markets for CO2 and there are different ways you can utilize CO2. So there are either conversion routes or non-conversion routes. So for the direct use of CO2, we can of course use it for yield boosting, say in greenhouses, to produce plants and all of this stuff. We can use it as urea and fertilizer, which is also a good approach to actually produce CO2. But also new applications come up. For example, we can use CO2 as the working medium in the supercritical CO2 cycles, which are much more efficient than conventional steam cycles, and that can of course increase energy efficiency and reduce our emissions in the first place. In terms of conversion, as I mentioned already, we can produce fuels and chemicals. So fuels, kind of projects that I'm working on is looking at how you can produce methane or methanol out of CO2 of course, using hydrogen from renewables. What we need to make sure is that when we convert CO2 into fuels, we take the full life cycle analysis in consideration to make sure that this process is at least carbon neutral. Of course, the best potential in terms of the climate is coming from the building materials, because essentially what you do is you produce building material, cement or something like this, from CO2, and then you actually lock CO2 in permanently, and that's what we want to achieve. We want to achieve permanent lock-in of CO2 over the lifetime. Looking at the scale and environmental benefit, of course, production of fuels will have the largest, largest potential to utilize CO2, mostly because we use so many fuels, transportation, energy, we use fuels every day. So that's the largest potential in terms of utilization of CO2 for now. But in terms of the relative climate benefits, it's kind of medium or moderate, I would say, because again, you would capture CO2, convert it into fuel, and then you remove it and again. So that could be a basis for carbon circular economy in principle. As I mentioned, relatively high CO2 use is to produce concrete or aggregates out of the CO2 and use that for building materials, building roads, or something like this. And this option has the largest relative climate benefit, mostly because you lock CO2 in. There are other opportunities for producing chemical intermediaries like methanol, or converting those later into polymers. But then again, we enter into another issue whether we should be producing even more polymers or plastic materials than we should be doing. So I hope this gave you a good overview of what direct air capture is, and what are the challenges, what are the current trends, and if you have any specific questions about direct air capture, I'm happy to answer those now or after this session. So let me have a look at the chat if we have any questions, and I'm going to answer those now. Okay, I don't see any questions right now, but if they will be coming, I will definitely make sure to actually answer those in the comments. So thank you everyone for watching. I really enjoyed this, even though we had a little bit technical issues earlier today, but I learned a lot, and that's the most important thing. Let's work together. If you have any questions about direct air capture, or if you would like to discuss potential collaboration in green energy transition area, feel free to reach out to me on LinkedIn. Feel free to connect and DM me. Thank you very much, and I'll see you soon.